Okay, welcome to Chapter 9, Predictive Modeling and Beyond of the Health Metrics and the Spread of Infectious Diseases book club. So very happy to talk about this second part of machine learning techniques. Because today we are going to make predictions about the future. And so we are going to see how to use models prediction on new data. This case is the case of, we continue what we started with the example where we use the MLR3 framework. So as you remember, we started with training a model and left few years aside to make predictions. So now what we are going to show is this second part. So we use the new data to test the model that we trained with MLR3. And so this is the first learning objective, so understand what means prediction. What is the difference with training a model. And then we have a look at how to predict and so evaluate future data that changes within time. And so to see how a phenomenon changes within time and be able to forecast, okay, new outcomes within the future. In time series analysis is the best way to go. And then we show how mixed models, and just the name is telling a lot. So we mix models. This is some different models. It's very useful for achieving the best. So what can be considered the best way, the best model to that it would be able to be closer producing results that are closer to the reality that it's unknown for everyone. So no one can predict the future with certainty. And there will be always a factor, something that can change what you expect it to be. So we are satisfied if we can achieve something that is very close to reality, and in terms of probability, that the probability it would be higher than expected, than in other case that things can happen. So we evaluate different models and mix them together in the hope to be able to achieve a high level of prediction, okay? Reality prediction, so future happenings prediction. Okay, so I already anticipated the challenging, okay, of applying a training model to new data. Okay, so something else can happen, something unexpected can happen. So, and the best, but I also mentioned about probability calculus. Okay, so by exploring the underlying patterns and analyzing historical data, we can expect to be able to estimate okay? In this case, disease burden, on very well, on a high level, okay? And so we can evaluate the impact and start thinking about how to calibrate intervention on popular health. Okay. So, as I mentioned it, chapter 8, what we did it, I don't know if you want to go back to that. We trained 2 models. We trained a GLIMNet, cross validation GLIMNet, and an XG boost with MLR3 meta package. Okay, this is the way we can do that. We can use this tool, which is to provide, I stated very briefly again, a framework for you to use machine learning. So again, a way to calibrate the parameters of each model that you choose, that they change it. So they change, these parameters are not always the same, and automatically. And it's a very good framework because it allows you to visualize what is the learner, what is the design of the models, and so on and so forth, as well as other meta packages. So we continue. So what we did was, let me jump into the chapter. And so what we did, this is the old data. What we did was training a model on all data before 2017. So the data were from 1990 to 2021. So we're taking 1919 to 2016 included, and trained our model. Okay, just imagine that we are now in 2016, and we have data since 2019, and now we like to see what's going to happen in the future. So, okay, so we're like going back in time. We already know what's happened and see what we can do. Okay, very simple, straightforward, just a reflection on just thinking about just putting down some thoughts on forecasting. Okay, and there is even a little very, nice thinking to put on the difference between prediction and predicting and forecasting. Okay, so just to mention a bit that there is always in literature very, very little differences. And so we are now back into 2016, and we are now predicting the future because we know what's happening. Okay, while forecasting is a completely new thing. You don't know anything about that. Okay, so we take the years from 2017 to 2021, exactly same data, and then grab our trained model that we save it in this object RR1. And this is the GLIMNet. And then the other, let me show you this way, because here I've just selected the two models. Okay, so RR1 and RR2. Okay, if you put a $sign, you'll find the learners, and you need to select the first one. So this is the syntax. okay, and then use predict on new data function. You put inside the new data and the task, specify the task, which is exactly the same. So this is we assign both prediction to an object. One is new pred and the name of the model, and the other one, so GlimNet and XGBoost. What's happened is that we can see, for example, for GlimNet, we already, I'm not going to data visualization because here you can already see how to make a visualization, but then we go back and start back with data visualization. So then, you know, when you study and you, this is what I usually do. I jump into a book. I'm not satisfied. If I like it, okay. Or if I need to study for any reason, I usually don't do it just one time. I go back and read it again. Okay, so this is a way that when you read the introduction to data visualization, then you can go back when you read the book to this side and see, now I can read it. Okay, this is something that very frequently happened to me when I usually study and get inside to a topic, to something. So you need to get inside that thing. And so we go back and forth on the things until we learn. And so I made this, this is you know, opinion, just a personal opinion, and it might be, can be done differently for certain. So this is a data visualization that I did it. I'm not going into it right now. Just have a look at the output. So this is Central African Republic, Malawi, and Zambia. The continuous line is the past. So up to we are now, so to the 2016. The red line, the brown reddish line, is the future that we don't know because we are in 2016, but we know because we are back from the future. So this is what is then what's happened. And the dotted line, dashed line, is our model prediction. I should put an explanation here because I just realized that I haven't specified those things, that the reddish line is that and the dashed line is the other. So I'm not sure if I'll be able to add that on printed edition, but I'll definitely change it on the online version. But you can even if you check the data visualization code, the snippet of code, you can see what is that. So we can see that for Central African Republic, the future is like a bit of not very close. While for Malawi, we guess it pretty fine, and Zambia, again, a bit of there is a bit of difference because you expected, we are talking about infectious diseases, and that is all fine. So if you are calibrating in health interventions on those numbers, but imagine that you are even thinking about modeling in general and you want to that number. So that number has to be that correct. So we are not getting the exact number. Okay, a bit more, a bit less, but closer. Okay, so obviously we don't know if we go forward and we like to, like, for example, create some synthetic data from 2000, here is 2021. Okay, let's say from 2025 to 2030, create some synthetic data based on some trends and things, and some factors, and we consider and see, apply these models, and we don't know what's going to happen. Okay. So, but then another important thing is that we can obviously consider the intervals, confident intervals. So that line is not just a line, but this is like a band that has a minimum and maximum level that you have predicted. That is confidence intervals. We talk about that. Okay. This is the GlimNet. While let's have a look at what the XGBoost did it. So pretty different. Okay, again, Malawi looks fine, but for the other two, it's not. Okay, so we can do some thoughts. We can put some thoughts on that, why Malawi is good, why the other is not, and so on and so forth. And so that's very interesting. Okay, so just put a stop in here for a second. We can go back in there with the following chapters where we do all in one go, like train the model and then predict on new data. But now think about what could be the best model to use, especially if you are looking at on a time frame, and you have you look at the data, and that this data is changing within time. So the best way to go is time series analysis. Time series analysis in some senses can be scared, but it is not, because as I said, modeling, it starts always with a classical function, y equals to beta 0 plus beta 1 times x. Okay, all the other models are adjustments of this base function. Okay, so even time series provides some interesting function that allows you to manipulate the data and identify underneath patterns. So in this example, we use ARIMA. ARIMA is a model such as XGBoost, GlimNet, this type of model. It is called autoregressive integrated moving average. So the name tells everything, what is happening inside this ARIMA. Okay, a moving average, I don't know if you know about that. It's integrated into this model that looks back into the past and look at the average within 2 days, 3 days, 6 days, 10 days. Okay, and put a stamp on it and say that is the average within a certain time frame. Okay, so then very important, I'm just so what's happening is that, let me see here. So time series can show you trends, and that means a trend is that you can identify if it's increasing, decreasing, or just a steady trend. So you can recognize immediately what is the trend of this data. But then it can show seasonality. That's very briefly. This can show seasonality. That means that a pattern is repeating within like a year, a month, a week. Okay, and so when you look at data that comes from that goes from 1990s to 2025, let's say, you cannot realize at first look what's happened, if there's any underneath pattern monthly, weekly, or every 6 months, or something like that. So seasonality allows you to go back in there and extrapolate. For example, if something happened within every 6 months, or every 5 years, or every 10 years, or something like that. And then you can put exactly define a cyclic pattern under this condition, or just random outcomes. Okay, so how do we evaluate these things? We apply decomposition. So there is a trend. This trend is decomposed and evaluated by the function. So we don't do that. Okay, so we use a model that does the work for us. So basically, takes the data and stop into months, year, 5 years, and things, and looks if there's something that repeats within the whole trend. And so we look at in the decomposition, we look again at the trend seasonality and these random things, and then apply the smoothing. That means we summarize this result with an average. Okay, this average is applied on what we found, if there's any seasonality on the cyclical pattern. So then we can try like a moving average over 3 years, 5 years, 10 years, but then we realize that this cyclical pattern is up, for example, every 5 years. So we apply a moving average within certain specified terms. Okay, and then we started applying splines, which means we I don't know if you following me what I'm saying. So then we apply exponential smoothings. Okay, so this can be done just with ARIMA, but ARIMA can be mixed with other models. Okay, let's have a look at this example. What we do here, okay, when we evaluate health data, in particular for evaluate the health status of a country, okay, usually what is taken into consideration is the level of the social demographic index, the SDI. It's very important, okay, and we can use it inside the model as an extra factor, such as the same as we use age, gender, or other things. So the SDI is very important as a very factor that is very important, and it is considered a key factor for evaluating the health status of a country, especially when because obviously if the social demographic index, just as the name as it sounds, if it's of a certain level, that means that the country is advanced and has a good health status. Okay, so we can use that as a factor for evaluate. But we will see a bit more. So in this case, for example, we are looking at the total fertility rate. Okay, for younger than 25 years old, and there is like this TFU 25, just to, because then this is decomposed. And so we look at this social demographic index and how we can like predict and have a look at this, how it went in the what is its trend, basically, how it changes and everything. So this is then the composite. It's composite of the geometric mean of the total fertility rate and the mean for those that are 15 years old and older, and lag distributed income per capita. Okay, what is this? These are the components of the SDI. Okay, the total fertility rate, the education for 15 years and older, and the income per capita. It usually ranges from 0 to 1. And so we start like having a look at this age-specific fertility rate, and because it is as well, you know, calculated in some way, and then use it inside the SDI. Okay, so we can see that each component is then normalized. And here it was a step that it was due because it's then with the SDI, you can always add the SDI inside your data when you build a model, and it allows you to even, you know, consider the status of a country, considering the level of the social demographic index of a country, as well as the spread of a specific infectious disease. Because if something is very well developed within a country, such as health measures on things, you can expect that that infectious disease will be immediately contained. So it won't be able to spread that much. This is a, you know, some reasoning. So we have a look at this social demographic index and see that we can apply it inside a model function. And so here we can load, just jumping to R and C, we can load the FPP3 package. And this package is very interesting. It comes with a amazing book, Forecasting Principle and Practice book. And if you have a look at the website of the book, they even provide short videos for you to like start reading the chapter. For each chapter, they're amazing. And so here we use this social demographic index from the 19 to the 19, and this is the HME data, Institute of Health Metrics and Evaluation data, which I extracted and put in the HMC package. You can see that with a quick visualization, how the social demographic index changed got better over time. So we don't see decreases. Obviously, if we go like restricting within time, within 5 years and things, we can see how this this little changes. But overall, we can confirm that the index is growing. Okay. And so a little of bit of data manipulation. and just apply this as TS-table time series. What does this function is just, you know, rename the vectors with a specific name that will be easily recognized by the model. And so we can use the autoplot function and just easily have a look at the evolution of the social demographic index in France, for example, because I haven't mentioned that I filtered, for example, for one specific location. Okay. And then what we do is applying a model. And this model is basically, what is this? Decomposing is this this function here. What does is basically decomposing the data, and within trend, seasonality, and cycle. As you can see, this is the model function, okay? And what's happening here, that it breaks the data into other factors, okay? So, and here is the result of the decomposition. So you can see that you have the value, the trend. This is the starting point, the real starting point. This is the trend. Here we cannot see much. This is not an example that you can see much. But and this the reminder are the random trends, okay? But and so here we can see that we can easily replicate very well with the model the pattern. What's happened with time series? Okay, this is an example. You have that book, and you can see that if you are interested, you can see that there's many interesting examples and things. But we should evaluate, when we do time series, the autocorrelation, and that means that something that can happen within a certain cycle. It's not said that it's worth it to evaluate. It might not happen in the following cycle. And so it's good to evaluate a bit of autocorrelation. And there is this function, ACF. And so we can see here there is a bit of work to do in it. But we can see that when these blue lines are basically define the autocorrelation. So if we are within these blue lines, we are good. If we go out, we are not. But this, and so we can calibrate our model based on the number of lags, because these are the lags, no? So the lags means 1 day, 2 days, 3 days, 1 year, 2 years in advance of your data. So for example, here is 1, 2, 3, 4, 5. We can say that we can consider 5 years lag, that things are repeating within 5 years. And so obviously, again, here what is provided is a tool, and the way I use these tools. And so you do some considerations, okay? Even here, I could have like expanded a bit on explanation, which I haven't. And So after having evaluated the autocorrelation, what I do is apply this function features, where I put the value and a specific type of feature in this case. And the same I do with just to see if there is some seasonality. And here I can see that it is not required to do that. Okay, so this is for this is manual. Again, it's used by the model, but in some sense it is manual. What we can just jump and do is use an auto-ARIMA model. The auto-ARIMA model does all these things and throw out a model that says, this is good. For example, in this case, I used the auto-ARIMA, used by just applying the ARIMA. So the FPP3, the Forecasting Principle Practice 3 package, allows you to use this model, this function model, and inside you put the type of the model. We already saw that in here with the decomposition. And so the components and things. And so we use again the model, but this time with the ARIMA. And this is without specifying anything else inside this function. That means that we are using the auto ARIMA. And this is auto calibration. And so it has auto calibrated to be 110. And you need to install this package as well. And this 111 means that we have, what is it? I think I haven't specified, just jump it in here. These things. Where is it? So these three elements that are inside that you can specify. Okay, you need to have a look at the documentation for that. And so it has auto-calibrated the model to be the best with 110. And it does provide the AIC values to see that they are negative. Then we can plot our forecast in the future with age specifying age equals to 10, so 10 years forwards in the future. And we can see that from 2020 and 2030, okay, we can safely say, hopefully, that is not steadying down, but it's keep growing up, going up. But I think it might be even too much in some senses, but in some sense. Okay, so something else that we can evaluate is partial correlation. And we do that because we talked about autocorrelation, but we can even see with this function PACF and then autoplot here if we are within the boundaries. And so we are within the boundaries and we are good to go. And then we can use this GG time series display to have them visualize all together. So the trend, the autocorrelation, the partial autocorrelation. So we can see that not so we haven't got any differences or surprise within the partial or autocoloration. So what we do now this is a time series applied with autoarima, very simple. Now what we do model ensembles, so mixed models. So we use more than one model inside our model function. We use the autoarima. As you can see, there is nothing. And then other arima that with some parameter specifications. Okay, we run the model. There are some other specific functions that are used stepwise and things. So basically, the model runs, but stop at center points and define an average and go forward to the other things. And so we collect the result of these 4 models. We order them with a bit of manipulation, pure long from the, and then arrange and select the models by BAC. Okay, we can see that still the best model is the one that is being thrown out from the autoarima, so 110. Okay, if we have a bit of forecast things with looking at the residuals. These are the residuals, and clearly a bit random. And we can see that we are within the boundaries, so we don't have to make adjustments or things. Just we restate what we said we said before. So even if we tried other models, still the autoarima is the best choice for this data. And then this is defined as model ensembles, and we will see more about these things. This ensemble means using different models, and there is a little difference between model ensemble and mixed models. Okay, so the model ensemble looks at the output. The mixed models use in, for example, estimating the ELD, looking at the effect, if they are fixed or random, and here I just re-mentioned what quite straightforward, but it's important because when we look at then, so we had a look at the social demographic index, because I mentioned that it will be very important as a factor to be used in the model. Then when we attempt to estimate the years lived with disabilities, for example, okay, and so that they are not fatal, that means that we are looking at not fatal outcomes. Something that is also very important is that is currently done is the current risk assessment. and it's something that is as well used as a K factor within the model. And here we see an example. So how to estimate tuberculosis. So the year lived with disability due to tuberculosis. So you're not died by it, but you have some consequences. And we load the incidence, prevalence, ELDs, and deaths due to tuberculosis. Do a bit of data manipulation to have this table. Okay, location, US, Italy, UK, Canada, Germany, and UK again. No, okay. So these are the 6 countries: US, Italy, UK, Canada, and Germany. And years are from 2010 and 2019. And we have deaths, ELDs, prevalence, and incidence due to tuberculosis. Okay, here I had to use the patterns because the book is going to be like grayish color, not color. Tuberculosis is different between 2010 and 2019 for each country, so it's definitely increased. And we also load the disability weights due to tuberculosis. And here we talked about the disability weights. So we need the severity and the disability weight. Okay, so the severity means we already mentioned it. If it's, in this case, it's an average value. So the disability weight in general for tuberculosis by any studies, if you look at, has been established to be 0.333. And so we can set our formula, model formula, to be prevalence plus year plus 1 and the location. So this is a interaction term that we use within the model, and use a mixed model. A mixed model, in this case, is the Elmer type of model, where we put the formula and the data. So what is a linear mixed model. Linear mixed model. And we can see some outcomes. We said that we have this standard deviation of 0.62 for by location. So a variation of 0.62, and residuals are 0.17. So we can see that it provides us with the criterion, REML criterion at convergence. So we have 34. And here is how the model looks with our new coefficients that we have estimated. So we have estimated the fixed effects of the model. We can extrapolate by the model with fixed effect function, and put this in the model function, and then evaluate the random effects. And again, you can see what changed, and then finally predict on this new data. So let's have a look at the visualization. So we can see that the US is above the line, for example, just to give you an example, while Canada is below. Okay, so this is predicted versus estimated. So on the x-axis, we have the ELDs, the values, and while on the y-axis we have the prediction values. So we can see that for example, the US is above and Canada is below. Just to give you an idea. So this is, we create some new data that are synthetic, fake, and predict using our ML, our model on new data. And we can see that there is some, we can, plot these things and just to see what is the impact of each year lived with disability for in each year for due to tuberculosis. And we can see that the US, so they are all decreasing. And so it's expected that in 2021 it's decreasing. And that is what is actually happening. So this is a different visualization than the others that are always shown in the previous chapters. And this, I done it just to make it differently than the others, because then you at this point seen that we did it before. This is my reasoning, the reasoning them. So that you should be able to visualize the thing as well, just as the same as we did it before. Because otherwise I would be same thing. But then to summarize, so predictive model is a valuable tool and things. So we have seen again other tools to use to forecast and predict the future. We saw how to predict something that coming back to the future. Coming back to the past. Okay, so we saw how to predict some things that we already know how it could go, and see how be certain to be able to evaluate the model. And then we talked about time series. Here is a bit more to investigate, to fully understand, but imagine that you know how to use it. You can like just revisit how to use the tool. And finally, evaluate the result of more than one model with model ensembles, and applied mixed model for evaluating the year lives with disability due to tuberculosis. I see that there might be some, I haven't used the SDI within this second example. That could have been like more reasonable, but we use it after in the following chapters. And so, yeah. Okay, thank you very much.